Okay, let's go, Lord, in prayer. Heavenly Father, we thank you, Lord, for what we've learned up till now, and as we finish this, that we can still dwell on your creation and what you've done with it. We ask that you open our minds and our hearts to what to continually seek for you. We ask all this in Jesus' name. Amen. Okay, let's begin. Let's listen to Dell. And this is John Whitmore. We met him. He's been on some of these as well.
Of mammals should tell us something.
Yeah, the very first bats that we find, the very oldest bats that we find are right here in this Green River Formation. And yet they have fully formed wings. They look like modern bats. And where in the world did they come from? Where are the transitional forms from the animals that gave rise to bats if the evolutionary model is true? And so one of the strengths we have in the creation model is that, you know, we can explain the sudden appearance of things like bats because we think that those would have been on the ark. And they didn't get fossilized during the flood, as far as we know. When we first find the bat fossils, they're in places like this, where they have the potential to become part of the fossil record here.
John, this represents a lot of your life here. You spent a lot of time working on your dissertation here.
I did. I spent some summers here collecting fish, studying the layers. This place is like home to me.
Uh-huh. Can you show me some of the stuff you were working with?
So we're in a commercial quarry here. It's a place where they dig these fish out and they sell them. And I think if we break some of these layers of rock open, we'll find some fish.
I'm hoping that happens.
Yeah. So what we're going to do is go in right along a seam right in here, and you can see how this whole thing is lifting up here. Yeah, it's a big slab. And just kind of get your fingers underneath there and lift it up. And so now what we're going to do is we're going to take some of these chisels. Yeah, we're going to split down through this,
Going down on it.
and see what we can find.
Is this what your research assistants did? Hold the rock while you...
That's right, all day long. Yeah, look at that, Del.
Oh yeah, look
Got
at that.
at least 3 fish here.
Yeah.
So there's one there, one right there, another one there, another one there.
Oh my goodness.
That was a good break right there.
Yeah.
So these all look like
Yeah,
maybe just a little herring type fish. Boy, that one is a really nice one right there.
It is.
Del, if you look at the edge right here, you can see multiple layers in here.
Yeah, I do.
And they're not very thick. They're almost as thick as
Yes.
playing cards.
Uh-huh.
And the conventional idea is that each pair of a layer, a dark layer and a light layer, lasted a year. But you look at fish like this guy down here, I do not see a single bone out of place. The fins are nice and splayed out right there. And based on my fish experiments, that thing sank down to the bottom of the lake and was buried in a calcium carbonate layer within a day after it laid down to the bottom. And I think that's the only way that you can explain such good preservation. And not only we see it there, but that fish, and that fish, they all have really exceptional preservation, and they have to be buried quickly.
Yeah, there's really just a lot of fine detail in that fossil there. So those small, tiny layers that we're looking at here, those are not annual layers.
I don't
Those have to
see
be
any way that they could be annual layers based
almost
on
daily.
how well they're yeah, I would think almost daily layers here. Something was different about the water chemistry here in that it was precipitating a lot of this calcium carbonate out, which was covering the fish. The other thing that's really interesting about this particular outcrop is there's several volcanic ash beds in here. And so the volcanoes are nearby, maybe some of the ones up in Yellowstone. They would erupt, and the ash would settle down through the lake, and here's this nice orange layer right here. That would be one volcanic ash bed. Here's another orange layer, not as thick. That would be another one. Here's another volcanic ash right here. And here's another ash bed that's maybe 1.5 inches thick.
Right.
These ash beds actually help us to tell time in the lake.
How's that?
if we can trace these ash beds and confidently know that they're the same from place to place in the lake basin, for example, we can look at this thickness between those two ash beds right there, and we know that that thickness of Green River Formation was laid down at the same time, whether we're right here in this spot or over at the edge of the lake. And it happens that we know these aren't yearly events because you can find this ash bed here, count the layers, find it at the edge of the lake, and at the edge of the lake, the thickness is more.
Huh.
And so
Is that more layers?
more layers at the edge of the lake, and that's because you have more sediments and whatnot coming in from the edge of the lake. And so we know these aren't yearly laminations. We know
Right, that wouldn't make sense.
the laminations are not equal from here to there. There's about 30% more layers at the edge of the lake than there is in the middle. And I don't know exactly how much time is represented between those ash beds, but one thing I do know is that the time is the same, whether it be weeks, months, or years between those ash beds. I know that there's the same amount of time. And so I was able to study the fish and the decay of the fish and the preservation of the fish during the same time in the lake's history. So I think the take-home point is that the fossil fish and the other fossils here show that these sediments were laid down rapidly. Yes, it was after the flood, but even after the flood, we have processes that produce fast layers.
You know, John, one of the things that has really impressed me is that you're not content with just sitting in an office somewhere, but you want to be out here looking at the reality to understand the truth and the facts. And I appreciate that about you, and that you understood you needed a PhD to help you do that. Is that important?
It is. At first I thought, you know, maybe why do I need a PhD? Why do I need to learn more? But the thing was that I didn't understand is how it would advance my thinking and how it would cause me to think deeper and consider other possibilities.
So would you say that for a young person who is considering one of these scientific areas, that it would be important, number one, to get their doctorate, and it's important for them to understand there's a whole lot of things to be looking at?
I think, Del, there's two things that are really important for a young scientist. And number one is to become well-trained. You need to interact not only with other creation scientists, but you need to interact with conventional scientists too. But the other thing, Del, is they need to be grounded well in Scripture. So they need to understand a biblical model, and they need to take things like this and put these kinds of things within the record. The biblical record doesn't tell us everything we want to know. It kind of gives us a framework, and we need the new generation to come up and begin to look deeper into some things. We don't know all the answers here yet. I would really like to know how much time is in between that ash bed and that ash bed. And we need some new scientists out here that are trained to think well, to work on problems like that.
One of the things I noticed about these scientists was the importance of teamwork. A key member of their team is a scientist named Ray Strong. Ray is a Canadian who has developed a special set of skills working in the oil and gas industry for the last 4 decades. Although I wasn't able to travel up to Calgary myself, we sent a team to interview him in his laboratory.
My wife told me one time she felt sorry for me getting up early in the morning and having to come into work, and I said, hold on a minute. I come to work and play. This is kind of the way the field of geology is. Every single sample that you look at is different. It has a different story to tell. It has different characteristics. There's always something new. I come to work and play every day. So we need to unbox the samples and get them prepared for cutting. Basically, what we're looking at are rock samples that have been collected in the Grand Canyon, and begin doing the technical rock analysis on those samples. This involves, first of all, thin section manufacture. And so this is taking rock materials down to the thickness that you can actually see through them. And this sample is very carefully labeled with an arrow pointing up, with top, and an identifier, which in this case is, there it is, CCF1, which is Carbon Canyon Fold number 1. But initially we need to cut these rocks, dry them, and get them prepped for thin section analysis. All right, this will be noisy. Okay, right now I'm going to put an orientation mark on this rock to show what end is up. That will be crucial to determine how the bedding structure is affected by how the rock materials originally were laid down. The sample is now ready for drying in preparation for liquid epoxy impregnation in this sample. Many professional geologists aren't aware of how to do this process. There are only a handful of people, perhaps in the entire world, who know how to do this kind of thing, at least to do it well. Literally a handful of people. Okay, the epoxy is used for stabilizing the sample, and if you fill up all the pore space with epoxy, you wind up, first of all, being able to identify where the porosity is, and secondly, you stabilize all the very fine material found in the pore spaces. So this is a high-pressure cell which we use to inject the liquid epoxy into the pore spaces in the sample. In the morning, we can retrieve it. The epoxy will be solidified, and then we can handle that piece of rock safely all through the rest of the next part of the process. It is important that we continue this work and that it succeed, because I believe there's a whole side of scientific investigation that has been largely ignored. And one of the aims that I have is to chase that particular pathway and look at data that may be not necessarily mainstream, but is very, very interesting and is significant. And so that's my endeavor in working with Andrew, for example, is to see what the data says and where there's supporting evidence to make sure that that's well documented. Okay, what we're doing now is taking the epoxy away from the bottom surface, and we're exposing the rock that's been impregnated with blue dyed epoxy. And so what that does is allow us to get a nice, flat, optically planar surface. And in this case, it's extremely important. We're not mistaking scratches for fractures. So we don't want to leave scratches in the rock surface. We want to make sure that all the scratches are out so that the fractures can be easily identified. Okay, so we're going to move on to the staining process, and then it will be ready for mounting to glass. We don't want to induce any kind of fracturing into the sample, and so mounting this to glass using the cyanoacrylate glue, crazy glue, ensures that we have a good stable surface with which to work. Imagine trying to work with a single piece of hair and trying to grind it without affecting the character of the hair. We want to make sure that we don't disturb the mineralogy of the sample as we go through the cutting and grinding processes. This slide we will now take to our grinding laps, where we'll thin it down to about 30 micron thickness. And this is kind of where the art comes into play. Do just a quick look in the microscope here, and it looks like we're pretty well at 30 microns thickness all the way across the entire thin section. We have the grains seen as being very clear. The material showing up as blue is empty space, and in cross-polarized light, if showing either as a gray or as a pale straw yellow. And that tells us that we're right on the 30 micron thickness. Back in the day when we were really busy, we would do anywhere between 80 to 100 of these types of samples a day. Personally, I've probably done in the order of about 20,000, I guess. Now we'll take the slide and look at it under the good petrographic microscope, which is a special kind of microscope made for analyzing geological thin sections. And then we move on to more elaborate testing methodologies like scanning electron microscopy. We'll take and gold coat the sample. Now, the amount of gold that we're going to put on it is very, very small, almost no value whatsoever. But it's necessary for conducting electrons along the surface of the sample in order to get the image that we want. It gives you almost a 3D visual image of the rock materials that you're looking at a very high magnification, which allows us to determine whether certain features are found in that particular rock. The electron beam runs down the column and is scanned back and forth across the sample. Okay, so we've got some very nice quartz cement showing up in here. There's some more quartz cement right there, but beautiful quartz overgrowths. Basically, the creation model provides alternatives to the explanations that are, in some cases, somewhat deficient. So looking at the creation model, for example, provided almost a stark contrast. Even though we were looking at the same data, we were quite often in disagreement over what the interpretation was to the data that we were both looking at. And I've watched this over my entire career now, as I've been involved in publishing of papers, presentations at professional conferences, and just seeing how that contrast plays out in terms of how people look at the world.
Well, there was a lot of analysis that still had to be done on those thin sections. But in the meantime, I wanted to get a better understanding of the forces that were involved that brought about those folds. And so I called my friend Steve Austin, and he suggested we go back to the Grand Canyon, but not to the bottom. But we needed to see it from the air because the forces are so large, they're so huge. You've got to get away, you've got to get higher in order to see it.
What a great opportunity to see all this. No better way to see the country than by helicopter. In overview, it's just a tremendous way to see it. Boy, what an amazing thing this is to come over this edge. Wow, unbelievable. You know, Steve, it's really the first time I've got this sensation of all the excavation, so to speak, in the Grand Canyon. It makes me begin to imagine that it was just solid layers all the way across. Yeah, you can imagine the continuity of strata through here. When you say the continuity, you're talking about the layers that existed on this side of the canyon. They exist on the other side, but now they're gone. You're looking for the continuity between the layer here and the layer over there. And that the strata were once continuous across where the canyon is now. And we're looking at the Kaibab Plateau. It's a large part of the Colorado Plateau that has been arched. It makes an arch structure that bends the strata. We have a name for it. It's called the East Kaibab monocline. So, Steve, when we talk about the monocline, we're talking about something forcing all of that massive material up, what are the forces that are causing that to happen?
Most creation geologists that I talked to suggested specific ocean floor that was shoved under western North America. The shoving of the ocean floor underneath western part of North America caused low density buoyant material to be down there, and then at the end of the flood it rose just because it was lighter and less dense. Than
That would push everything above it up.
It will push the plateau up higher.
Yeah.
Notice, here comes the arch. Okay, now look for this. Look for the strata and how they're bent.
Oh yeah, I see.
Okay, so we're looking down this flexure along the East Kaibab monocline, a line where there's been a lot of bending of the strata.
You see it all the way up there.
And the strata are horizontal, and all of a
Right.
sudden they go vertical.
Yes.
Notice, it looks like soft sediment deformation. You can see the strata as they're horizontal, and all of a sudden they turn 90 degrees. Isn't that amazing?
And they're not crumbled. They're folded. Like soft taffy.
Now, as we come over the top of this, we're going to see Carbon Canyon down there.
Yes.
So the monocline forms this soft sediment fold structure.
And everywhere we see that monocline, we see the bending rather than the breaking. Is that correct?
It's extraordinary, but this is kind of normal Colorado Plateau monocline. Okay? So the rock was not hard when it was flexed. It was soft. But there may be some other faulting in here. It may behave brittly afterwards.
If we find it where it's broken, then that would indicate those layers had already hardened.
Yeah, we're seeing the sequence of sedimentation and tectonics very closely associated in time, not separated by hundreds of millions of years.
Yes.
In other words, tectonics and sedimentation occur together, not separated by geologic ages.
And when you say tectonics, you're talking about the movement that
Uplifted
uplifts
the
the mountains and the plateaus
Yeah.
and all of that. And so if the sedimentary layers are soft while that is happening, then we'll get those bends and folds.
Yes.
That makes sense to me. Well, I have to at least comment on the beauty of all of this.
Yes. Notice, again, the difference in elevation.
Yes.
We're flying below the elevation of Kaibab limestone on the north rim of Grand Canyon on the right side of us here.
But it's way below us over
And
here.
it's
on the
way
other
below
side.
us on the left.
Yeah.
It drops in elevation along what? That monocline. It forms the barrier, the arch structure here. That's ultimately why we have the lake basin that was able to fill and then spill through the Kaibab upwarp, I believe, to form the Grand Canyon. I can see that the scum on the surface there, that's the tufa deposit. And that's the bathtub ring of the big lake that was filled in this basin. Can you imagine a lake in this basin up at 6,100 feet elevation, making that bathtub ring deposit?
So all of this in front of us, this was all covered with that lake.
We call it Hopi Lake.
And it comes up to a natural dam up here.
Yeah.
At this point you're talking about. And that's where at some point, for some reason, it breached. It just gave way, or maybe an earthquake or something.
Just overtopping of a natural earth dam can create
Which is
spillway
rapidly
erosion.
eroded.
And there's no such thing as slow failure of a natural dam in spillover. When spillover erosion occurs on a natural dam, it erodes rapidly.
Where do you think this is occurring in terms of the flood?
I like to think of it as post-flood. The rock is already hardened. The monocline has already been flexed. The upwarp has occurred. the rocks are hardened, and then the overtopping and spillway erosion of the solid rock.
So this could be 100 years.
Hundreds of years after the flood,
Afterwards.
possibly.
How many different lakes are we talking about?
There may be 3 or 4
Three or
different
four.
lakes associated with the Grand Canyon itself. So above Lee's Ferry in the Lake Powell area, Capirates Plateau, behind that another lake, that could fail. And my view is the lakes failed from the top down. The spillover of this Hopi Lake over the Kaibab upwarp into the next basin below it created what? Another lake below it, and that would be Toroweep Lake. The drainage basins upstream filled first, and they spilled, destroyed their dams by spillway erosion, and they drained to the west. And you created the Grand Canyon by top-down failing of dams into lowland areas. So the erosion is channeled to form a canyon. Okay, and it's a straight canyon, but yeah, it's channelized, and that is what we see. So we see erosion in channels by spillover, it looks like. And so the lake didn't take millions of years to drain. It didn't take millions of years for the Colorado River to erode the Grand Canyon.
And you know, really, Steve, I can look around and at least imagine, envision, this wasn't carved out by a river. This is the kind of thing that you see when massive water just floods and it just evacuates all of that material.
And thinking about breach dams and the notching of the plateau by spillover, that is the latest geologic rage in thinking. The old way of thinking about Grand Canyon is, it was eroded over millions of years. No. That's becoming unpopular among geologists. In fact, as I talk to geologists, very few geologists are defending that way of thinking. They are going to something freaky and catastrophic like overtopping of lakes.
Right.
There's an ice age lake in Montana that failed through an ice dam across eastern Washington into the Columbia River Basin. A huge failure there.
So, Steve, let me step back here for a second and talk about these lakes again. There's a massive amount of water represented in what we're looking at here. Is that caused from the huge amount of precipitation that was occurring as a result of the warm oceans, or is there some other source for all of that water?
Well, I like a warm ocean at the end of the flood. You could have a rainy period for hundreds of years after the flood. We could fill these basins with rainwater, and then they spill and overtop the landscape. And wouldn't that be a great place to survive after the global flood? Next to a nice big lake with lots of water and well-irrigated landscape.
Until it breached.
Until it breached, yeah. Okay, and then today it's rather arid,
Yes.
isn't it?
If you had lakefront property here, it all went away quickly.
Yeah, there could be palm trees. There's evidence here of camels, of geese, shorebirds on the lake. There's evidence of pike minnow. The bathtub ring right there next to where the failure point is, that's icing on the cake. That makes it real to me that the edge of the lake was up there next to the breach point. So what we see makes a strong case for some kind of catastrophic deposition of the strata of the Grand Canyon, a giant global flood, if you will. The very quick bending and upheaval of the strata forming the Kaibab Plateau, and then in the post-flood period, the spillover erosion of the plateau. In other words, we have the pieces of the puzzle
Yes.
that seem to assemble themselves. So we have an explanation. It's a hypothesis with extreme explanatory power. And it's consistent with the framework of the Bible.
A lot of us don't realize the amount of time and effort that it takes for a scientist, once they have done all the field work and all the lab work, to bring everything together. They now need to write it up. They need to put it in a form in which the general scientific community can look at it and review it. So we had the opportunity to go back to Cedarville and sit down with Andrew and John to discuss their findings. We talked not only about what they had found, but also about the implications of their research.
It's paper thin.
And are these all the slides that Ray
Yes,
sent?
he sent them to us in boxes like this, and you can see what they look like. They're just, but of course, these were hand delivered. He came down at a meeting that John was attending and hand delivered. You wouldn't trust these to the postal
They'll
service.
send them through the mail.
I can
And
understand
then
that.
John came and delivered them to me.
So is this what you have then under the microscope?
Yep.
Yes.
How long have you been studying these?
Well, I've literally spent months, going screen by screen by screen, moving the stage backwards and forwards, systematically going through each slide, taking photos, recording details.
Hundreds and hundreds of
Yeah.
hours under the microscope.
And I've got thousands of photographs at different points. Every time I took notes, I took a photograph so I could go back to that.
So after these months and months of looking at these thin slides, what did you find?
Well, I've put this on the screen deliberately because this is a sample that comes from right in the bend of that major fault in the Tapeats sandstone. And so it's a good test case, because if there ever was going to be a sample that was going to show the mechanical or the metamorphic effects from slow, gradual heat and pressure changes and moving around, it would be this sample. So let me walk you through it. First of all, you can see that those white grains.
Yes.
Okay, the really white ones, that's the mineral quartz, which is window glass. Okay, we can see some of these spaces are still there. This is the blue, highlighting these spaces. Well, in this instance, what happened, more quartz grew, and you can see how it's joined these two grains together, and you can see that little sharp point there.
Yes.
This quartz cement, it's grown into that space. So what happens is, when it's deposited, there's water in between those sand grains, but the water has chemicals dissolved in it. And so when the water dries out, those chemicals precipitate and fill in all the spaces between the sand grains and harden it, making it a cement.
So that cement is like glue. It holds the grains together. So sand in a sandbox would be really loose, but if you put some glue in there, or what geologists call cement, that's what kind of holds the rock together and makes it hard.
What does it tell you when you see that?
Well, it's in pristine condition. It hasn't changed. This is in the hinge of that fold. You'd expect when the folding occurred, millions of years later, supposedly, that cement should have been disrupted. It should have been crushed.
Okay.
And maybe it would have to regrow again, but you'd still see fracturing that was healed. But you don't see that in any of this. You still see the original pores.
It tells us that the cement was added after the rocks were bent.
All right, so we were talking earlier about breaking and crumbling of a very hard rock from a larger standpoint. Now, what you're talking about is you look at the small pieces, you also would find crumbling.
Yes.
But you don't see that.
No, that's right. You can see where grains have been compressed close to one another, and you can still see the original outlines. Here's some more cement over here that's joined that grain to this grain.
So let me ask this question then. Is that the cement formed after it was bent, not before?
That's right.
Right.
Now, you also took samples a long way away from that fold, and you wanted to look at those and compare those to in the fold. We haven't seen one of those. Do you have
I've got
a
one
slide
right
of that?
here. Okay, one right here. And it has exactly the same features. Now, we're going to have to adjust this again. Let's get it back into focus, because we can move it around. Okay, you can see there, again, you've got the same. You've got the blue spaces, you've got, look at all the different sized grains of the white ones of quartz, you've got feldspar, you've even got some rock fragments there. So, It doesn't look any different.
So let me put you on the spot here, Andrew. If I were to mix up a slide from the fold and a slide, how far away? Was it
This one here, that was above Little Colorado River. So as the crow flies, 5 to 6 miles.
Okay, so if I were to switch those up and put them under the microscope and say, Andrew, is this from the fold or is this from 5 miles away? Could you tell?
I couldn't tell because there's no radical difference.
tells you
They're
something.
essentially the same. And that was
Okay.
the whole point of taking those
Yes.
samples to be a control.
The fact that we find them the same, every sample of the sandstone has exactly the same features, is quite telling. It means they folded before they hardened.
Well, let's go back to the conventional paradigm that would say that the folding took place as a result of a metamorphosis in the rocks. What would this look like if that had occurred? Would it look different, and why?
There would be a whole set of different features that are not present here.
Yeah, metamorphic rocks under the microscope look distinctly different from this. Here's a slide that might even look closer. When you take a sandstone, which is the type of rock that we found in that fold,
Yes.
and you put a sandstone under metamorphic heat and pressure, it's going to look something like this. This rock is called a quartzite. The dominant mineral here is going to be quartz. And one of the things you notice right away is that there's not any blue in there.
Right.
And that means that all the cement has grown in between the grains. You can still see some of the grains in there. I think, Andrew, if you put it under cross-polarized light, the grains show up even better.
Here's where we look at under cross polars.
But you can see how these grains interlock with one another, just like pieces
This
in
is
a
the
jigsaw
puzzle you were talking about.
That's right.
And here's the
Turn the
puzzle
light
put
up
together.
a little bit more, and you see how
Very
you've got
different.
lots of these connecting points, these junction points that are often, 3 grains at what we call a triple point.
So, Del, we think if the conventional paradigm were true, that the rock samples we took out of that fold would look more like this than the sample of sandstone that we looked at.
Well, to an untrained eye, I can tell you this, it is a radically different picture than what we saw. So it makes one think the current paradigm is not correct. Is that what you're
And
assuming here?
you can see why it was important to
Yes.
make the thin sections and to look at because you can't see these effects in a hand specimen. You've got to really dive into these grains at this microscopic level, and all geologists do this. It's part of the detective work. You have your framework of thinking and you say to yourself, well, if I go and get samples, what do I expect to find? And you set up some questions to answer and what you expect to find. And then you go out and you do the tests to check whether, and if you don't find what you already predicted you're going to find, you're going to have to change how you
Change your model.
Try and change your model
Sure.
for how you understand these rocks.
So what are you now waiting on from Ray?
Well, Ray is also going to talk to us about the results he got from using a scanning electron microscope, which is going in an even higher power of magnification. This is just in 2 dimensions. He's able to look in 3 dimensions. You'll be able to see the quartz cement, the way it's grown between the quartz grains. And that'll tell us whether there's been any mechanical disruption or whether the cement has occurred as the last stage in the whole process.
Okay.
There we go. Oh, hello, Ray. It's so good to see you again. And unfortunately, we got to do this by Zoom. And I have in my lab today, Del Tackett is with us.
Hey, Ray.
And, Andrew Snelling is
Good
with us.
to see you again, Ray. It's hard to believe. It's nearly 2 years since I was up there last with you in the lab.
I know. I was just looking at some of the images that we were doing while you were up here, and looking at the dates on them, and it's hard to believe.
So, Ray, we want to look at one of the thin sections from the tight fold in Carbon Canyon. And here's the thin section. And one of the things that struck me right away when looking at these thin sections was the amount of porosity in these rocks. Even at this place where the bend was really tight. There's still a lot of empty space in there. And Ray, could we look at an image from this very same rock sample, sample number 10, and let us know your observations about what you see with the scanning electron microscope.
So here we have an example of a scanning electron microscopy image. If you can see my cursor here, that's a sand grain right there. And associated with that sand grain are a number of overgrowths of quartz.
Ray, when you say overgrowth, what do you mean by that?
Okay, this is actually the cement. The important thing to look at here is that the individual overgrowths that you see here have not been disturbed. Their contacts have not been disturbed by any kind of mechanical deformation.
So we're actually seeing that the cement hasn't been damaged because you've got these pristine ends of the crystals as they've grown on the original sand grains.
So that shows that the bending took place and then the rock became a solid.
Exactly. And of course, this is at a much higher magnification, so any even subtle deformation would show up between these cemented particles.
So Ray, that sample was, as you know, from the Carbon Canyon Fold in the hinge, and that was in the tapetes. It's probably going to be helpful now if we look at a regional sample. So that's TSS3. We might want to just look at that too, because that's a long way away from these folds.
So there's an awful lot to see in this particular image, but the overgrowths are basically two types. We have beautiful quartz overgrowths, but you've also got precipitation of clays, which lends to, I guess, what you'd call the dirty appearance of this particular rock. The overgrowths that you see here are quite pristine, indicating that they've been growing into open pore space. I don't see anything unusual here. These rocks haven't been dislocated, haven't been fractured, all those sorts of things.
So I asked us earlier of Andrew, if we were to put several of these pictures, if I were to mix them up, would you be able to tell me, you know, which belongs in the hinge and which does not?
No, I couldn't.
And it seems to me that that is, from my perspective, kind of the summary of this, is it, and what you wanted to see in the very beginning.
Well, the sequence is sedimentation, folding, then hardening.
That's correct. Now, you can help me here because it seems to me, from a very amateur perspective at this point, that we're looking at a very significant finding. Anything that begins to show that a theory is wrong is a major observation. And I'm almost getting a little deja vu here back when we were looking at the soft dinosaur tissue. We were looking at something that from the conventional paradigm's perspective should not be here, right? The soft dinosaur tissue should not be here because it is millions and millions of years old.
There's no mechanism to preserve it for millions of years.
Correct. And now we're looking at a microscopic level of the grains and the cementation and all of these things that we've been looking at. And we're seeing from a conventional paradigm perspective what shouldn't be there. That to me is fascinating. Yeah. And I'm excited to be here, yeah, to share that with you.
And it kind of blows the mind to think that we're looking here we've looked here at the microscopic level, but it gives us a narrative to explain, you know, the building of mountains. Mm-hmm. So it's quite dramatic because, as you say, you know, just these observations under the microscope help us to put the pieces of the puzzle together in the chronology and when these mountains formed. It wasn't hundreds of millions of years after the layers were deposited. It was only months after the layers were deposited. And that's a radical departure from
Yes.
conventional explanations of the building of mountains.
I'm reminded of a trip that was organized for the heads of our international oil and gas company. Part of that was a helicopter trip over Jasper, Alberta. Well, there are massive, massive folds in the Rocky Mountains. And one of the individuals who happened to be an engineer, long time standing with this particular company, he later recounted to me, he said, I saw all these folds in the rock. I can't even imagine how you could think that those would have been formed in solid cemented rocks. They had to have been soft when those big folds were formed. So it's critical to state that we're looking at scientific evidence. We're not imagining this stuff. We're actually looking at scientific evidence that supports a particular model, one of a young Earth and short events that made the features that we observe.
Ray makes an important point. There really is a lot of evidence that supports the creation model. But we've only been able to show you a brief summary of just one research project. Even in this documentary, there were many conversations we had to leave out, details we couldn't include, scientific evidence that took too long to explain. But my hope is that you have a new appreciation for how creation science actually works. I also hope this film reminds you that Genesis is the best explanation for everything we see in the world around us. I was fortunate enough to meet up with Andrew one more time at my home in Colorado, where I spend every day under the shadow of an enormous mountain.
So Andrew, looking back at all that we've talked about and all that we've looked at, you're still in the process of this whole research, right? How many papers have you already published?
2 have already been published. The 3rd is in the process of being published, and there's 4 more to come. And so those papers are long and detailed with all the microscope photographs and all the descriptions of the rocks, because it's reporting all the observational data that anyone can go and look at and read.
I guess the question is, how is the world going to respond to that?
So if they were to admit that my evidence indicates there was a catastrophic global flood with a short period of time of catastrophic processes, a humongous amount of energy and earth movements to raise up these mountains, they're going to have to forget their millions of years. So they're going to have to reject their own interpretive framework. So they're either going to ignore the research, which is what they commonly do, or attack the scientists.
And yet you still go on. You still proceed in this work.
Absolutely, because it's part of our worship. As we've been given dominion over the earth by God, we've been given brains to use. He expects us to use them. It's an act of worship to Him. And of course, we've got a lot more work to do. I mean, what about the animals? What were they doing at this time? What about the people that were descended from Noah? There's lots of questions that we have yet to answer, to link from the time that Noah got off the ark with the rise of the mountains into the civilizations that everyone is familiar with. So we've got a lot of work ahead of us to get a fully integrated package of explaining the world around us as it is today.
So that brings me back again to some things that we've talked about before. We talked about them earlier in the previous film, and that is the whole notion of creation scientists and the processes that a creation scientist goes through, and that has all been exampled for us in this project.
Well, anyone can collect rock samples, anyone can do laboratory analyses, but they're just numbers, they're just observations of minerals. You've got to be able to put that within an interpretive framework. And I start with the interpretive framework that Genesis is literal history, that God has given us that written account of history, and it describes the Genesis flood. And so then I start to look at the data, the observational data within that framework. And so that's what creation scientists do. We ask questions and then we do the research to see if we can answer those questions, but all within the interpretive framework of Genesis.
Andrew, there are still a lot of questions that are left unanswered. Where do you see creation science going from this point forward?
Well, actually, I'm quite excited because we see another generation being raised up for which we can hand on the torch. And, you know, my research and others who are doing research like this are setting examples for the younger generation. We want to equip them and challenge them with the things that have yet to be answered to take up the questions and run with it and do the necessary research. So I'm quite excited about what God can do with young people in the years ahead.
So it just, in the back of my mind, I'm sitting here going, those scientists that are not creation scientists must have known this. There's no way that they couldn't know that, because they look at the same stuff that they do here. And I think what they did here as far as creation science is complete. I mean, that was a lot of work. I mean, months and months and months of work doing it. So, I mean, what's Satan known for? A little bit of truth, the rest of it lies. And he's got a great audience, huge audience. They're still teaching this stuff. They're still teaching that the Colorado River is going through there and do that. There's no way. There's just no way that you can look at it and say it's such a massive hole. Where did all the rocks go that were pulled out of there? We asked Nate Loper, the guy that was with us, working on his PhD and stuff. He said, when you take a look at it, you would figure that the Colorado goes out and then it makes a direct turn south out of the canyon. But so you would think that a lot of the rocks and whatnot would have been down in the Gulf of Mexico there, or not Gulf of Mexico, Gulf of California there, that it would have been deposited down there. It did not. When it came out of there, it just went right to the west into the Mojave Desert, and that's where my mom and dad wintered. So when I went out there to see that, you could see these great big red rocks just sitting out in the desert all over the place there. And he said, Los Angeles is built on the red limestone rock that came out of the canyon. So it the force of where all those red rocks went direct west through a path through the mountains somehow. So take it with a grain of sand, I guess, instead of a grain of salt. But what do you think? I mean, where do you land on this with what we've seen over the last 20 weeks now? 21 weeks? 20 weeks? 20 weeks, yeah.
Well, you mentioned Psalm 104, but you also think of Psalm 19, where that means declare the glory of God. From a man showed the signs of work. It's pretty, I was just curious as we talk about, like the Grand Canyon and the Rocky Mountains. I just wondered how would it compare if they looked at rocks, for example, in Australia, the Great Australian Bight, or Mount Everest, or Mount Kilimanjaro. How would those things be there?
They see the same thing. They see that they were all soft, and they aren't crumbled. When you see those rocks go straight up in the air like that, and they're not crumbled, it had to be soft when it came through. And can you imagine the plate coming through there? I mean, it's almost, earlier in the thing, he said, you can see that it's almost half of the nation, that plate came underneath, and it must have been moving to do that. So it's like that no matter where it is. I mean, there's several, the Himalayas are so big because several plates are underneath that. Ones coming up from India, China, the ocean. But it's just, you know, and some of the other things we saw with the things like these, you know. It can't take millions and billions of years for this stuff. You don't see evidence of transitional forms where if you're thinking about evolution, that's key to them. They don't have them. When they're shown in the fossil records, they have the complexity there. There's nothing to build onto that. I mean, they have some things that change over time. There are mutations, but most of them aren't good mutations. Most of them go the opposite way. But you can't see that or hear that in the news because they don't want you to know that. Yeah, they don't want you thinking on your own, and that's the reason why they wouldn't allow them to take these things, because they knew what they were going to see and find.
A side issue to this is that came to what struck me was, we can see what God did with water.
Water and the movement of, I mean, all
Yeah.
sort of things. You got the magma coming up, heating the oceans, making it so that you have an ice age to,
Yeah.
and
If God can do that with, yeah, I'm saying it in a way I don't mean it. God can do that with a little water. What is he gonna do with a little fire? It's coming up.
You don't wanna know.
It's reserved right now for fire. And he did this with water.
in a year,
Yeah,
so, you know,
yeah.
it's, but I think there's enough evidence from what they've already showed me, here. I'm not, I wouldn't say to call myself as a scientist, but, I think they've done enough of their homework to actually prove out a lot of things that it does say in the framework of the Bible. So, but, I mean, that's the whole case for why you don't see that on the other side. They're not giving us the full scoop, because they can't. Then they would have to admit that there is a higher power, as we all do. So, I'm gonna put this up there again, if you guys wanna take one of these home, to watch, just go right ahead and do it. They're gonna be up in that spot. I watched them, I wouldn't say hundreds of times, but a lot of times, because there's little tidbits I pick up more, while we're doing that, so be my guest.